Hello, I'm Jia-Ju from Tsinghua University. I'm very glad to share our paper about the detection of unsafe DMA access. DMA is a popular mechanism for improving hardware I/O performance, and it has been widely used in modern device drivers. DMA provides direct data transfer between hardware registers and system memory without CPU involvement. In this way, the CPU can focus on other tasks without caring about hardware I/O. For each DMA access, there are three basic steps. First, the driver needs to create a DMA buffer. Then the driver performs a DMA access like a regular variable access. Note that this is different from hardware register access, which is performed by calling specific interface functions like read-L and inb. Finally, the driver needs to delete the DMA buffer to avoid memory leaks. Overall, there are two types of DMA buffers used in device drivers. One is streaming DMA buffer. It is synchronously available to both the CPU and the hardware device. Namely, there is no automated synchronization between hardware registers and CPU cache. Thus, the driver needs to explicitly perform synchronization. As a result, each streaming DMA access is relatively cheap. The other is concurrent DMA buffer. It is simultaneously available to both the CPU and hardware device. There is automated synchronization between hardware registers and CPU cache. Thus, the driver doesn't need to explicitly perform synchronization. As a result, each concurrent DMA access is relatively expensive. Both of streaming DMA access and concurrent DMA access can have security risks. For streaming DMA access, due to no automated synchronization, the driver should not access the content of the DMA buffer until this buffer is mapped. There is one exception, namely the driver is allowed to access buffer content during synchronization with hardware registers and the CPU cache. If this rule is violated, the data between hardware registers and CPU cache can be inconsistent, which can cause hardware or driver malfunctions. For short, we call such violation as inconsistent DMA buffer. Here is a real example of inconsistent DMA access in the Linux driver. In the figure, the streaming DMA buffer SKB arrow data is created, and then its content is read via the variable HDL arrow frame control without any synchronization. Thus, an inconsistent DMA access occurs here. This problem was first introduced in Linux 4.4 and fixed by us in October 2020. For concurrent DMA access, because the hardware device can be untrusted, it can write bad data into concurrent DMA buffers, which are used by the driver. Thus, the driver should perform correct validation of the data from buffers before using the data. If this rule is violated, the DMA data can cause security bugs, such as buffer flow, invalid pointer access, and so on. For short, we call such violation as unchecked DMA access. Here is a real example of unchecked DMA access in a Linux driver. In the figure, the concurrent DMA buffer adapter arrow_ISSConf is created in the function mx3 probe device, and its data is used as an array index where the variable n in the function vmxnet3 getISS. When the hardware device is untrusted, the variable n can be very large, which can cause buffer flow. This problem was first introduced in Linux 3.16 and fixed by us in June 2020. In summary, there are some basic rules for streaming DMA access and concurrent DMA access. If these rules are violated, unsafe DMA access can occur. In device drivers, there are three main challenges of detecting unsafe DMA access. The first challenge is how to identify DMA access. On one hand, as mentioned above, each DMA access is implemented as a regular variable access without calling specific interface functions. On the other hand, DMA creation and DMA access often have implicit execution order from static code observation, namely in a broken control flow. The second challenge is how to check the safety of DMA access with good accuracy and efficiency when analyzing large OS code. The final challenge is how to drop false positives, because validating code path feasibility is often difficult and expensive. To solve these challenges, we propose 3 key techniques. First, we propose a field-based alias analysis to effectively identify DMA access from driver code. Second, we propose a flow-sensitive and pattern-based analysis to accurately and efficiently check the safety of DMA access. Finally, we propose an efficient code path validation method to drop false positives and reduce the overhead of using an SMT server. Now let's see how to identify DMA access. There are 2 steps. In the first step, we handle DMA buffer creation. Specifically, we identify function calls about DMA creation and collect the information about their return variables, including variable names, data structure types, and fields. In the second step, we identify DMA access according to the collected information. Specifically, we check each variable access in the driver code. If variable name and data structure information matches the collected information, the access is identified to be a DMA access. Note that in the 2 steps, we use an intra-procedural, flow-insensitive, and still alias analysis to handle variable assignments. Now let's see how to check DMA access. For streaming DMA access, we check 4 patterns about DMA operations, which are shown in the figure. Specifically, we perform forward and backward flow-sensitive analysis of the driver code to check these patterns. For coherent DMA access, we first perform flow-sensitive taint analysis to identify the operations affected by DMA data, and then check security problems with 3 patterns, namely whether the DMA data affects bad loop condition, array index, or pointer access offset. For each possible unsafe DMA access, we validate its code path feasibility to drop false positives. There are 3 steps in code path validation. First, we translate each instruction in the code path to these 3 constraints. Second, we add additional constraints that can trigger security bugs. For example, we add a constraint about array bound to check possible buffer overflow. Finally, we use these 3 to solve all the constraints. If these constraints cannot be satisfied, the possible unsafe DMA access is identified as a false positive and is dropped. Based on the key techniques, we propose a new approach named SADA to statically detect unsafe DMA access in US drivers. We have implemented SADA with the Clone compiler, and SADA performs static analysis on the IRM bytecode. In the evaluation, we use SADA to check the driver code. In Linux 5.6, we just check the kernel directories, drivers, and sound, which contain driver code of the kernel. The table shows the detection results of unsafe DMA access. In total, SADA finds 284 real unsafe DMA accesses. Among the 123 inconsistent DMA accesses, 108 of them are caused by direct access after DMA creation, and 15 of them are caused by incorrect DMA synchronization. Among the 161 unchecked DMA accesses, 121 of them can cause buffer flow. 36 of them can cause invalid pointer access, and 4 of them can cause infinite loop pooling. According up to the paper submission, 105 unsafe access unsafe DMA accesses have been confirmed by driver developers. However, SADA still has some limitations. On one hand, SADA reports some false positives for some reasons. For example, the current alien synthesis is still simple and not accurate enough. Moreover, the pathway addition can make mistakes in complex cases. On the other hand, SADA may have false negatives for some reasons. For example, it lacks the analysis of function pointer calls. Moreover, it neglects other patterns of unsafe DMA access at present. Now let's conclude the work. DMA is a popular mechanism used in modern device drivers. However, it can still introduce safety risks in practice. To detect unsafe DMA accesses in device drivers, we propose a new static approach named SADA, which uses 3 key techniques. In the evaluation, SADA finds 284 real unsafe DMA accesses in Linux 5.6. Thanks for listening. If you have any question, please feel free to contact us.